Greetings. I'm Yvonne, Staff for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. There is much concern about the rising heat of the world's oceans and how that might cause the collapse of major ocean currents. Our guest today is an expert who uses historical data for the analysis of ocean warming. Hali Kilbourne is a research associate professor at the University of Maryland Center for Environmental Science. Her research adds an important dimension to the worldwide scientific attempts to predict what will happen to the vital ocean currents that are absolutely necessary for climate stability. Dr. Kilbourne, welcome, and thank you very much for joining us.
Thank you. Thank you for having me.
Okay, and to start with, could you give us a little general background? I think that this whole business of ocean currents is not really well understood at the public level. Could you give us an idea of the importance of ocean currents, these big currents?
Well, so I think that the ocean currents in general transport heat throughout the climate system. That's a physical role that they play is distributing heat from the warm tropics to the cool poles, and part of that is they also distribute a lot of other things like nutrients that ecosystems depend on, and carbon in the ocean. And actually, the deep ocean has a lot of dissolved carbon dioxide, so that if that circulates to the surface, it actually is a major control on atmospheric carbon dioxide and greenhouse gas concentrations,
yes,
which affects our climate.
Yeah, that's very important. The other thing is a lot of these currents, a number of these currents that are so important are sort of global, right? Or they feed into each other and therefore they cover the globe. Is that correct?
Yeah, they're part. The ocean is essentially one ocean on a rotating sphere of an Earth, and so they are all connected and basically driven by that rotation and the winds, and yeah.
Okay. Okay, and I just want to make that clear that it's very much a global process, that it's terribly important for the climate of the Earth, and also, as you said, distributing nutrients and so on. Could you tell us anything a little about the increased warming over time now, and then we'll get to your work on this?
Well, do you mean warming in regards to its impact on ocean circulation, or just what's going on in the
one of the things that comes up a lot is that there is warming. So in this Gulf Stream, they mentioned it's warming and it changes things, or if you prefer, it's the atmosphere. What is the present
what's going on? Well, so humans are putting greenhouse gases into the atmosphere. That atmosphere then warms up and warms the ocean.
Good.
But the ocean, remember I said that the ocean's role is to circulate heat.
Right.
So it absorbs energy
Right.
from the sun, and it transports heat. And so when you have changes in ocean circulation, you can have changes in the amount of heat transported from one place to another on the Earth.
Yes.
So that it might cause warming or cooling in a particular location.
Yes.
Because of the heat transport. But that's sort of an effect that happens because of ocean circulation. But then there's the global effect of greenhouse gases that is generally warming the Earth.
Right, right. And then the interesting thing about what you do, and you don't see this very much at all, is that you've taken a very deep, historical approach to this. I think your focus is the last 2,000 years, and what would be the significance of that? Why is that important? It seems important.
Well, so I'm a paleoclimatologist and paleoceanographer, and I do study the last couple thousand years. There's multiple reasons to study the last couple thousand years. Number one is it puts our modern changes in historical context. What if essentially what's happening to Earth right now, and we only know what's happening if we know what was happening before. A topic of very much interest in my field is how does changes in mean climate impact the year-to-year variability that we have in the climate system. Some people might know that we're having an El Nino year this year, and that's a major driver of interannual variability. And a major question is what's going to happen to El Nino in the future? And it's hard to model, and one way to answer that question is, well, how did it behave in the past? So that's one basic reason I'm interested in the recent past, is putting that historical change, or putting modern change in historical context. There are also lots of questions we can ask about what we are currently doing to the environment. One thing that has come up, I was working on a synthesis project with many colleagues. We got together and tried to put together everything we know about the last 2,000 years in terms of temperature change. And what we found was that the warming, we have records of warming from these natural archives that indicate the Earth was warming pretty much as soon as we started putting greenhouse gases in the atmosphere, which makes total sense. But we actually, because our widespread measurements of temperature by thermometer really didn't start until the mid-1800s. The modern climate scientists who worry more about recent decades were only looking back to the mid-1800s. But when we actually have globally distributed paleoclimate records, these proxy records of past temperature, we see that actually the trend actually probably started in the mid-1800s. So the modern people who study the modern system, who were really only looking at the mid-1800s as a pristine time, it was already not pristine in terms of the Earth's climate and human impacts.
Right, but 2,000 years ago or 1,000 years ago, where you might have had warming or these changes, was there a difference than warming and cooling periods?
Yeah, so the magnitude of change of the last century is unprecedented in that time, or even the last. Well, it's unprecedented in Earth's history, quite honestly. But the period before the last, say, 200 years was an era where the natural system was in effect. We didn't have humans burning greenhouse gases, or emitting greenhouse gases to nearly the extent that we do now, and therefore the main processes that were driving variability in the climate system were just the natural processes of the system.
Right.
And that's what we study in order to understand what's happening in the future. So we have to understand what the natural system does first.
Right. Understand, I'm going to come back to that sort of abrupt shift there. The mid-1800s Industrial Revolution gets started, and we start messing around with things here. That in ancient times, there were these cooling and warming periods. They refer to them as periods of time, like the Little Ice Age and this, that, some other of these terms, the medieval cooling period, and so on. But it's not clear what was happening in the ocean in general. Did it affect oceans as well?
Yes. So that big synthesis that I told you I was involved in, we found the medieval warm period, it actually was a warm period, was maybe warmer in some places of the world, and the Little Ice Age was in fact slightly cooler. We think now that was because of a series of volcanic events that occurred sort of back to back, so to speak, and then impacted the Earth's climate during that time period. So there certainly were small changes, but those changes were the magnitude of change was very small. relative to what we see today.
Right. And the ocean circulation systems were not as dramatically affected as you might anticipate now, or did things shut down like they
interestingly, so the variability over recent centuries is until the most recent, I should say, over the last couple thousand years, was muted, both in ocean circulation and general the climate variability in general. It was a time of stability, actually, and I mean the historians have long attributed to the rise of human sort
right.
of cities and civilizations and agriculture to the fact that we had a very stable climate. So since the last ice age. Now, before that, over many thousands of years, tens of thousands of years, we had ice ages going in and out, and that caused changes in ocean circulation and global temperatures that were not nearly as fast as what we're seeing today, but they were of large magnitude.
Okay.
Yeah.
Right. So that did matter back then, but it was a different cause altogether, and it was a very, very long time ago. So that's an important point. And then now, more recently, and one other thing, there were El Niños presumably in the distant past, but they wouldn't have caused maybe as much difficulty as now with what we're doing to complicate things.
Well, I mean, El Niños have occurred in the past. We have evidence of that, and the only difficulty is that humans are dependent on agriculture. I mean,
yes.
Other systems aren't necessarily. Other systems have evolved over time to be able to withstand regular variability. It's not a big deal. It's only our rigid systems that have trouble. So it's really a human problem.
Yeah, right.
Not a natural problem.
Right. That's what I want to just get very, very clear, because that seems like that's what your data have established very well, that, look, there's a very big difference here in terms of periods of change in the past are quite different from what we are seeing now. And you pointed out there's a more abrupt, a more rapid change now as well. And so this seems to be very important. Now, what would happen as a result of these currents changing, slowing down? How would that affect the global climate? And then we'll get into what we are doing to mess things up here.
I want to just clarify. So I mean, one aspect of ocean circulation that I study is the deep overturning circulation in the North Atlantic. So these are waters that come from the South Atlantic, cross the equator to the north, and this process transports heat, and they get cold and lose buoyancy and sink to the bottom in the deep North Atlantic. And so that's an important part. It's only a component of the ocean circulation system.
Right.
But it is thought to be, it's an important part because of its transport of heat, and it's a major transporter of heat, and it's important for nutrient cycling and carbon cycling. And so that current system is predicted to slow down under warming conditions. It's driven by heat and salt imbalances in the ocean, and therefore the warming actually impacts it. And so with a warming of the North Atlantic, it's thought that essentially it won't sink as much, and therefore there'll be slower cycling of the circulation. So that it will have it could very strongly impact fisheries. It will have impacts on carbon distribution between the ocean and the atmosphere. It has implications for sort of mean temperature in various parts of the ocean. And so there's a lot of things that are connected to it. We find today that a lot of fisheries and fish populations are connected, seem to be follow boom and bust cycles that are thought to be related to this circulation system.
Right. I want to just clarify a couple of things here. That's the currents in question. Recently, we're hearing a lot about the Gulf Stream current, and I think that connects to the AMOC. Is that what you were talking about, the AMOC, the Atlantic Meridional? Is that where?
Yeah,
Yes,
AMOC being
that's
Atlantic
a huge
Meridional
one.
overturning circulation.
Yes, I know, you can hardly
and the Gulf
remember.
Stream, AMOC is, I guess, a component, a part of the AMOC flows in the Gulf Stream.
Yes.
We won't turn off the Gulf Stream ever, because the Gulf Stream exists because of the fact that the Earth is a rotating sphere. It's an ocean on a rotating sphere, and the physics of that actually control the Gulf Stream.
Okay.
But this AMOC is driven by heat and salt distribution.
Great point.
That is what can change. So it's a component of the Gulf Stream. So if AMOC slows down, then the Gulf Stream will slow down.
Yes, okay. Right.
So
thank you for that. And does that affect like the cooling and warming on land, like in Europe or in this on North America? Okay.
Well, an important part of that heat transport is that the AMOC brings essentially energy from the southern hemisphere to the northern hemisphere, and as part of the Gulf Stream, heat is brought to essentially Europe, and it basically, the ocean warms the atmosphere in the North Atlantic, so that southern England is much warmer than it otherwise would be, because and Scandinavia as well would be much colder than it is today, than it is now, if that heat were not transported by the Gulf Stream.
Okay, so that's really the currents play a huge role in the general climate of the globe, of the Earth, right? If I understand that, then, and then with this happening, there have been studies like on the AMOC and stuff for a long while. There seems to be uncertainties. A lot of people and scientists have to be cautious and so on, but they say we're not sure yet. Is that what you think as well? Whether it's slowing down?
That we're not sure yet whether AMOC has slowed down or not.
Right.
And there's definitely there's some controversy. Different scientists look at different data and have different confidence in different aspects of it. I think many physical oceanographers look primarily at the observations, and really we started observing AMOC intensely in about 2004.
So it's recent,
It's really only a very short time period.
Right.
And before that, we only have sort of some physical oceanographic measurements of some components of AMOC, but not the full picture, so to speak.
Right.
And so then the interpretations become a little less certain over the 20th century, and before that, we don't really have oceanographic direct observations, and that's where paleoceanography comes in.
Right. Thank you for that. That's a really important clarification, because it's hard to understand from the public view sometimes, why are people cautious about this? Is it yes or no? We need an answer right now. And it's just not that simple. And that takes us to how you collect your data. And especially since you have this historical perspective, could you tell us what you do to go out there and collect your data?
Yeah, so paleoceanographers in general use sort of natural archives. Many of us have a geology background, so they're often geologic archives, and in those archives, and I'll give you an example, is a sediment core might be an archive. Marine sediments. Actually, I'm a specialist in using coral skeletons, fossil corals, as an archive. But these archives have physical, chemical, and biological changes in them that we measure and quantify, and we relate to the environment at the time that the archive sort of was laid down. So for instance, with a fossil coral skeleton, fossil corals actually, or corals have annual bands like tree rings. So I can count the rings and go back in time. And the chemistry of that skeleton reflects the chemistry and temperature of the ocean in which that coral grew.
Oh.
So I can tell you about whether an El Nino happened in a certain location or a certain year, because I know that in that location where that coral grew, El Ninos cause warmer conditions, for instance. And so I can see the spikes in temperature that happen every few years, and look, those are the El Nino events. So that's what paleoceanographers do. We look at those physical and chemical evidences of past environmental change. So I got into studying AMOC because I was seeing changes in the radiocarbon concentration. So C14, many people have heard of C14 dating. Well, we also use it as a tracer of different water masses in the ocean because they have different ages. And so we can see the different aged water coming by our coral. And so we were seeing changes in the ocean circulation from the radiocarbon data that were coinciding with the temperature and salinity changes that I was seeing in other chemical variables I was seeing. So that's how I even got into understanding this connection between the climate and the mean climate temperature and the ocean circulation changes.
Right. That seems invaluable, to have that. I had no idea it was such a good indicator. I think most of us outside here wouldn't realize that corals preserve a climate record, a record like this. So this is extremely interesting. Do you have any other sources, or do you focus primarily on the coral?
So I mean, we all have our specialty, but paleoceanographers in general, I have colleagues who specialize more in sediment cores, and I have I've collected my fair share of sediment cores and looked at it too. And sediment cores are a major archive for paleoceanography, for oceanography in general, because essentially plankton in the ocean are constantly raining down, and the chemistry of, say, the organisms in the plankton they record just like a coral. And similarly, the organic matter can tell us about nutrients and nutrient cycling, nutrient availability.
Yes.
So there's a lot of information that we can get out of those sediment cores. A direct measurement, quote unquote, of the bottom currents as part of this AMOC circulation. One thing we do is we measure the grain size in those sediment cores. So when ocean currents go along the bottom, they'll maybe winnow the fine sediments away, leaving only the heavy sediments. So when the currents are strong, you have more of that winnowing. And when the currents are weak, you have less of that winnowing. So you can actually measure current speed along the bottom from grain size in a sediment core. And you do that down core, and just like the coral with the annual rings, you go down through time.
That is amazing.
Yeah, but we only have a sediment core from one location, one part of the ocean, and we take another sediment core in another location, in another part of the ocean. So we get this picture. It's a little bit, paleoceanography is a little bit like the story of the blind man and the elephant, where one feels the tail and feels something, and one feels the trunk and feels something else, the other feels the side and feels something else. So it's no wonder that paleoceanographers sometimes disagree about what they're seeing. Because we're specialists in various things, and we're often looking at a piece of the puzzle. And that's why we have these big discussions about what we're seeing, to try to come to consensus about what the state of the system was actually doing. And so that's where we are with AMOC, is trying to, we're looking at different pieces of the puzzle, of the elephant, and trying to put the elephant together, trying to put the picture of whether or not this ocean circulation has slowed down in recent centuries. So the idea from physics is that with global warming, we will see a slowdown. The question is, well, if we've been warming, do we already see a slowdown?
Yes, yes. This is terrific. I think this would be enormously appealing to a lot of students starting out today if you could see these fabulous records. And apparently they're full of information and accurate information. So it's a question of getting enough out there, getting people to put their data together and so on. But do you find that this is quite appealing to students today? Are you attracting?
Yeah. I think a lot of students want to make a difference
Yes, and this would.
in understanding climate change and helping the world deal with climate change. So it certainly appeals to some students who have been exposed to it, because it's somewhat esoteric. Not everybody gets exposed to it to
Right.
even know it's out there as an option. But certainly the students who find out about it and hear about it are excited about it.
Well, the other thing I was thinking was that you have this is sort of integrated in terms of different fields. You need chemistry, you need physics, you need oceanography, you need all of these things. And it would be extremely interesting to study this phenomena in that manner. But I would think for a lot of young people, and you mentioned there's a cause to it as well. You're contributing something that's very important today that's quite great, but I can see the appeal for sure. In terms of the implications right now, given the data right now, and people are being cautious, but they are concerned. I think scientists are concerned. Do you think in terms of any adaptations that we can make, or obviously the preventive would be stop the fossil fuels, stop what we're doing to cause the problem, but do you think in terms of what should we do?
I mean, the lowest hanging fruit, the easiest thing to do is actually to change our behavior with regards to burning fossil fuels.
Yes.
It really is the easiest thing to do.
Right.
We humans do not have the power to just like wave a wand and change ocean circulation.
Yes.
It took centuries and a lot of fossil fuel burning and a lot of digging and a lot of effort.
Right.
To cause the problem that we're causing now. And so the easiest thing to do is to actually stop the cause, which is to stop burning fossil fuels. It really is as simple as that,
Yes,
unfortunately,
yes.
or fortunately.
Right, and right now, not 50 years from now.
Because not in 10 years, not in 20 years, but now.
Exactly. The other thing is the fossil fuels and big agriculture, a number of those things that are contributing, we could stop or we could alter the way that we do things quickly. It is possible, and so thank you for bringing that up. And then before we go, one more thing that I forgot to mention before. What about the freshwater aspect, like the melting ice and so on? How does that affect the oceans? Can you tell us in terms
Yes. So I described how this AMOC circulation is driven by heat and salt. Well, so we talked a lot about the heat part, but actually salty water is more dense. And so when you melt a whole bunch of glaciers, say off Greenland, then you end up with a lot of fresh water in the ocean, and that makes the sinking water at depth to be less dense, and so it's harder to sink. So it's both warmer and less dense, and fresher and less dense. So it's a bit of a feedback system. So once we warm the Earth, we contribute to multiple processes that cause change.
Exactly. So we are making a bit of a mess of things, aren't we? Okay, that's settled. But in any case, it sounds as though your work is cut out for you in the future, and it's a huge contribution. I hope you'll find a way to get it out to the general public more graphically. Do you know that people can understand this kind of work that you do, which is a tremendous contribution and seems to be very important in accumulating the data that we need at this time. So the very best of luck on that score.
Well, thank you for having me and giving me the opportunity to get it out there a little bit more.